So we have two types of potential energy. One coming from the external force, the other one coming from the internal forces. Assuming that both types of forces are conservative. Okay. So this result will not hold if we have a non-conservative force. But for the moment, let's assume that everything is conservative. So if we have such a condition, maybe I can erase this one. So if you have such condition, then I can define the total potential energy. Yeah, the total potential energy. So the U total is just the one coming from here. Okay. This is just the okay. I'm just writing it down like this, yeah, in order not to. Sorry, not maybe not quite from here. I mean, I can define a total potential energy at one point. Yeah, at one point. So this is just coming from the external plus half. Yeah, plus half of some ij. Yeah, 1 minus delta ij of u ij. So basically, it says that the total potential energy is just the potential energy coming from the external plus the total contribution from the internal. Okay. Now, so we have this expression. We can continue working on this expression. Yeah, the kinetic energy. Okay. See, the kinetic energy can be written as like this. All right. So there is one thing okay, maybe there is okay, let's just work here. Remember that the last term, yeah, the last term, we have sum of I times, so this is just basically Ri prime dot, yeah, and this is dot producted with capital V. But we know already from our previous derivation, yeah, that this is just zero. Okay, remember, this is just zero, or actually the zero one is okay, let me just make it more specific. This can be written as a d dt, yeah, of mi ri prime. So everything is dotted with capital V. Now this is zero. Okay, this is zero. So the only surviving terms are the first and the second. Yeah. And now you can see that the well, the first is not zero, yeah, because this is vi prime squared. So before inside the summation, we squared the ri prime dot. So it's not necessarily zero. We don't have any theorem to support that this is zero, yeah, unless, I mean, unlike this case here, we prove that this is zero. But for this one, this is not zero. Okay. So now T can be written as, now let's take a look at this. And the second term, the summation is over m is over I, so it goes the summation is for m only, yeah, because the capital V doesn't have any index on it. So this is just, I'm going to write down the second term as the first one, capital M, because sum of mi is this capital M, the total mass, times the capital V squared. What is this? What is this?
Kinetic energy of center of
Kinetic energy of center.
Right. This is the kinetic energy of the center of mass. So if the center of mass is moving along with the system, then this is the kinetic energy. It's kinetic energy. Plus the second term, the kinetic energy of each particle, right, with respect to its center of mass. Okay. So the kinetic energy has two contributions, one from the center of mass itself, and the second one is from all particles with respect to the center of mass. Okay. Okay, I don't really care the expression as long as it can be written like this. So we can actually, since this is the equality, right? The left hand side is just equal to the right hand side, the whole right hand side. So basically, we say that T2 minus T1 is equal to U1 minus U2, right? But then this again shows that T1 plus U1 is equal to T2 plus U2, since the total kinetic plus potential energies are the same for point 1 and point 2. In general, it should be the same for any other point. Yeah. So for what I mean is that the total energies should be the same everywhere, and then we again end up with the conservation law of energy, mechanical energy, right? So now here we prove that a system of particles will conserve its energy as long as all the forces are conservative. Okay, if the forces are conservative, then the energy is conserved for the system. And one of the application of this is when you, well, application of all these conservation law for the system of particle is like when you have a bomb or a firecracker, yeah, that explodes in the air. Okay, or rocket maybe rocket that release its some of its stages in the air, yeah. So you see, when you have like for example a bomb that is maybe it's in the air and then it explodes. Now when it explodes, there is no external forces, yeah, and there is and we assume that the forces are a conservative. So when it explodes, we have two pieces or more than two pieces of this original bomb, but then they will move with several velocities such that the total kinetic, so the total linear momentum and total energy is conserved. Okay. All right. Question? So okay, so I think that is so much for the what do you call the first topic of our course, yeah, that is the conservation laws. Okay, but the conservation laws. Now we have time, so I'm going to go into constraints. All right, so basically what we talk about for this whole week is that Newtonian mechanics is a study of the dynamics of a particle or a system. Yeah? And to study the dynamics, we can use the Newton's equation. Yeah? the Newton's equation, we have learned that this is just the mass times the acceleration, and then here you put every forces involved here, right? Whether it's external or it's internal. Okay, so basically, once we know all the forces, yeah, the premise here is that we should be able to know the system, or in other words, we should be able to solve the equations of the motion for the system. And solving the equations of motion amounts to knowing the behavior of the system for any given time. Okay, indefinitely to the future. Right. The question is it correct? Okay. Well, this is, yes, this is the equations that we need to solve for the behavior of the system. But in most cases, knowing the equations or knowing what forces involved in a system is not sufficient. Yeah. Or another way of saying it, there may be forces that we cannot know, that we cannot express as an equation. Okay, but those forces still affect the behavior of the system, or even those forces are the one that somehow constrains the motion of the system to be in a specific behavior. And that's why those forces can be called as the forces of constraint. In other words, besides knowing all the forces involved, we should also know the constraints of the system. Okay, so that's where the constraint comes. So what is a constraint actually? What is the definition of a constraint? Well, no, judging from the name, we can loosely define the constraint as everything that restricts the behavior of a system. Okay, and this can be almost anything that we often overlook, that we often take it for granted. Yeah, when we observe a system moving in a certain behavior, sometimes we don't realize that they move in such a behavior because of the constraint enforced to that system. Okay, so sometimes we overlook the constraints, or sometimes we just take for granted the constraint, so we don't really think about the constraint. Now, the advantage of knowing the constraint is that sometimes we can solve the system, or sometimes we can solve the equation of motion of the system more easily, or even without having to solve the equations of motion. By just knowing, identifying the constraints, we can at least have a qualitative description of the behavior of the system. Let me give you an example. Right. Suppose this is a incredibly simple example here. Suppose I have a particle, let's say, yeah, that is placed on the surface of a plane, yeah, but the plane here is inclined, so the plane makes an angle. Let's say the angle is let's say alpha with respect to the ground or the horizontal plane. Okay, so this is basically motion of a particle on an inclined plane. This is very simple Newtonian problem. Yeah, you solved it even in high school. Now, the from our empirical observation, yeah, for such a system, we know that the particle will always move on the plane, yeah, unless there is a force that we specify that makes the particle goes off the plane. That makes the particle go off the plane. There is no reason why the particle should be off the plane, so the particle will always be moving on the plane, yeah, in this case, the inclined plane. So let's analyze the system using the force diagrams. We know that there is the the force that goes up, and this is just the normal force, okay? And we have also the force that goes straight down. So what I mean by goes up is this perpendicular to the plane, yeah. But also there is a force that goes straight down, yeah, to the center of the earth, and this is what we call the weight, okay. Is there any force involved? Assume that the inclined plane is perfectly smooth, so there is no friction and there is no air resistance as well. Yeah, suppose that we are doing this experiment in an idealized environment. So there's a vacuum, there is no air that can make air resistance. Also, there is no friction. The plane is perfectly smooth. So what will happen to this situation? Well, we can write down the equation. Yeah, what are the equations of motion? Let's take um, this to be the y direction and this to be the x direction. So the x goes here, the y goes here. All right. So now we can always decompose the forces. Yeah, you can always decompose the forces into its y and x components. So here is just the ny, yeah, n of y, and here is just the n of x. Oh, sorry. This is the n of x. The same thing for the mg. Yeah? The mg can be decomposed into come on. Oh, I cannot put here. Okay, let's just put it like here. Okay, this is just the mg of well no, I don't have to do that, sorry, because mg is already along the y direction, so there is no component of mg along the x direction, okay. Yeah, so now we can use Newton's laws, yeah, this law. So for x direction, what do we have? For the x direction, there is only one force involved here, right? So we have this particle has mass. There's only one particle, yeah, along the x direction. So we have x double dot, yeah, and this is equal to nx, and nx is just the minus n sine alpha, yeah. Minus because we take the right direction to be positive, and so consequently the left direction is negative. How about the y component of this force? we have m of y double dot. This is just, now we have two forces, yeah, because we have n of y minus mg, right? And this is just n of cosine alpha minus mg. So we have two equations to solve. All right, so far so elementary. So far so elementary, but then how many functions we should find, we should solve? We need to solve for x, for y, and for n, right? Because n is something that comes as a consequence of the system. So here, the particle is rolling down the inclined plane, so it induces the normal force. So we need to find the normal force. We need to find also the x position and y position for all time. So in other words, there are three unknown functions. Okay, we have three unknown functions. There are x, y, and n, but we only have two equations. Okay, so you know what happens, right? If we have two equations to solve for three functions, then the situation is not determined. Yeah, at least there is one function that cannot be determined. Yeah, this situation is what we call the undetermined system. Is on the other hand, we have more equations than the number of functions to solve. That situation is called the overdetermined. In both cases, this is not good. Both cases are not good because then we cannot determine uniquely each unknown function. Okay, each unknown function. Question? So this is what I mean by my previous statement, that just by knowing the equations of motion is not enough. Because here we know the equations of motion, there are two equations of motion, but these equations of motion cannot be used to solve the functions, because we have three functions. Okay, and so in other words, our equation of motion is not sufficient. We need one more condition. So here is where the constraint plays a role. What can we extract? What information can we extract from the concept of constraint here? Well, apparently this simple problem is undetermined problem, seemingly, yeah. But if we look closer, there is one piece of information that we haven't used actually. What is that piece of information that we overlook? Well, the fact that the particle can only move on the plane. So the particle cannot move off the plane. That's the piece of information missing in these equations. Okay, and that is the constraint. Yeah, the particle is constrained to move only on the plane. The particle cannot move off the plane, like jumping off the inclined plane and go back. No, the particle cannot do that. So here the constraint that we often overlook is that the particle can only roll down the plane. Now we can use that constraint to our advantage actually. So let's write down the constraint. The constraint here is, so how can we express this constraint in a mathematical term? In a mathematical term, how can we express this constraint? Well, since the particle can only move along this one plane, even though it has 2 degrees of freedom, yeah, along x and along y. So consequently, x and y are no longer independent to each other. Yeah. Well, when writing down these two equations, we assume that x is independent of y and y is independent of x. But now we know that it's not the case. Yeah, because the particle cannot move arbitrarily in x while at the same time moving arbitrarily in y. Yeah, the trajectory of the particle is determined only along this path. So there is a mixing between x and y. In other words, that there is a constraint between x and y. So what is the constraint between x and y? We can easily say that x and y are related through this equation. That y is just x times tangent alpha, right? In other words, the equation of constraint is that x minus x, y minus x tangent alpha is 0. This is the constraint that we overlooked. This is the constraint that we didn't take into account in our previous analysis. Okay. Now using this, obviously we can solve the equations of motion easily, right? How do we solve it? Well, take a look at the constraint and take the derivative twice for both sides. So we can write down that this is y double prime, this is just x double prime. Since alpha is a constant, so it doesn't, the derivative doesn't do anything to the tangent alpha. The tangent alpha is just constant coefficient here. Right, so now instead of having 2 equations of motion, we only have one. Okay, we only have one. Sorry, yeah, we only have one equations of motion. And then we can put, sorry, I was wrong. Instead of 3 unknown functions, I'm saying we only have 2 unknown functions. Yeah, because x is related to y. Okay, so I can find, I can pick any of x or y, and then the other one is determined, is fixed. Okay, so the only unknown functions are y and n, or x and n, either one. Okay, now what do? I can put this constraint into the second equation. So I have m times x double dot tangent alpha. This is just n cos alpha minus mg. Right? And I can use the first equation to substitute for n. Right? I have the n here is just minus m x double prime over sine alpha coming from here, right? So then I can insert this expression into here. So what do I get? This is minus mx double prime over sine alpha minus mg. So I can bring this to the left hand side, yeah, to join it with this one. So I have m x double prime. I have tangent plus 1 over sine. Okay, so this is just tangent is sine per cosine. This is 1 over sine. So I have this one is sine alpha cos alpha. We have here sine square plus cosine square, right? And this is just minus mg. Well, we can easily cancel the m, and this numerator becomes 1. So what is left is that x double prime is just minus g times sine alpha times cosine alpha. All right, so we only have to solve for this equation, and this equation is easy to solve because g is constant, alpha is constant. So you can just integrate it twice, you get x as a function of t. Once you get x as a function of t, you can either calculate y from here and n from here. So now you get all the solutions you need, right? Question?
No, Pak.
Okay, so let me give you another example of constraint. Suppose I have a ball or a bead. Yeah, I have a bead of mass m, and it's rolling. You know a bead, yeah. A bead is like a particle that is pierced by a wire. Now the wire makes the loop a circular loop like this. So this is the bead. So the bead can only move along this wire. Okay, the wire has a radius. Wire has a radius r. Okay, and of course it has theta, right? Now the bead, since it has mass, so it has m times g, sorry. And now also the bead, since it cannot, well, this is the constraint, right? The constraint is that the bead can only move along the circle. It cannot move off the circle. Okay, it cannot fall down to the center of the circle, nor it can jump off the circle. So the bead has what we call the normal force, yeah, along this one. All right, so the situation can be pictured like this, yeah. If we just ignore the circular loop, we have here we have here, then we have here. Okay, this is n, this is mg, right? This is theta, like this. All right, so let's write down the equations for the bead. Well, since it's a motion in 2 dimensions, we have also two equations of motion. Yeah? The first one is along the x direction. Along the x direction, there is only component of the normal force. Yeah. So the same actually, mx double dot is just n times cosine theta, right? Because the component of n that goes here is just the n times cosine theta. What about the vertical component? The vertical component, we have m of y double dot. So there are two contributions for the forces here. One coming from the y component of the normal force. The other one is coming from the weight. So this is just n times sine theta minus mg. Very simple. But as you can see here, well, the problem is that we have to find for x, y, and n. Yeah, so there are still 3 unknown functions. we can employ or we can utilize the constraint. Yeah, the constraint here. What is the constraint? Or in other words, how do we translate the constraint mathematically? So I think the most challenging topic or the most challenging step in using the constraint to help us solving the equations of motion is that how to translate the constraint in mathematical form, or how to translate the constraint in mathematical expression. I think that's the most challenging part. Yeah. Because once you get that, the rest is just mathematical. The rest is just technical, right? You know the formalism, but how to translate the constraint into mathematical form? That's the physics challenge, yeah. And that's very challenging. Yeah, sometimes it's easy, sometimes it's very difficult. Okay, and that's the art of physics. Yeah, the art of doing physics. Now you see here the constraint is such a way that the particle can only move along a circle. So now we can see that there is once again the dependence of x on y, or the other way around, yeah, of y on x. So x and y are no longer independent, they are related. How are they related? Using the circular equations. So the constraint equivalent to saying that x squared plus y squared is equal to r squared. This is the constraint. Okay. Now, how do we write down the constraint? I mean, this is the constraint, but how can we insert the constraint here? And well, one way of doing that is using the polar coordinate. So I can write down like here r cosine theta and y is r cos sine theta. Now I can put it here. So now, well, now the variable is now theta. Yeah, r is constant, so theta is the one that is a function of time. So when you take the x double dot, so x dot you have r theta minus r theta dot sine theta. But when you take the derivative once again, you will end up with this r times minus r times theta double dot times sine theta minus r theta dot squared times cosine theta. And also we have y is just r theta double dot cosine theta minus r theta double dot squared sine theta. So these whole equations can be expressed just in terms of theta, okay? Just in terms of theta. And then we can also extract n from here. We can extract n from here. N is just mx double dot over cosine theta, right? X double dot is here. So n is just minus m r. We have theta double dot. Sine divided by cosine is just tangent theta minus plus, sorry, cosine divided by cosine is 1. So this is theta dot square. Okay. So put everything. Let's insert this into the y double prime. Okay. So the y double prime here is just m r. Here I have theta double dot cosine theta minus theta dot squared sine theta. This is equal to the n times sine theta, but n is here, so this is minus mr theta double dot tangent theta plus theta dot square minus mg. Okay, so I can cancel m. Actually, I can cancel mr, yeah, but let's cancel m first. So I can rearrange this equation, yeah. Is there anything I can cancel here? Well, not yet, but I can collect the terms which have theta double dot, yeah. So here I have r theta double dot. What are they? Cosine theta plus tangent theta, yeah. Right? So I can bring this to the other side. So I have r theta dot squared sine theta. So this is sine theta plus 1. Oh, no. What did I do wrong? What did I do wrong? What did I do wrong here? No. Oh, sorry, I forgot. I should multiply this with sine theta, yeah. Okay. So this is just cos tangent theta times sine theta. Okay, let me just write down like this. This is n times sine theta minus mg. Okay. Now the left hand side is just r. Sorry. R of theta r theta double dot, yeah. Sorry, r theta double dot, we have cosine theta plus tangent theta sine theta, yeah. Now I can bring the theta dot square to the other side. I have r theta dot square sine. Oh, sine theta cancels, yeah. All right, so this one cancels, right? Yeah, this cancels with that. Okay, that's good. So I have here minus g only. Well, this can be written like, what is this? Sine over cos times sine, so sine squared over cos. So we have cosine squared plus sine squared over cosine theta. So it's 1 over cosine theta, right? So theta double dot is just minus g over r times cosine theta. All right, so this is the equation of motion. Okay, this is the equation of motion. Solving this, we can get the n and we can get the x and y, right? Now, if you notice in these two examples that I gave you, that the force of constraint in these two examples is the normal force, right? Because that's the force that exists whenever the constraint is enforced. In other words, if you take off the constraint, for example, you can just turn off the constraint, yeah. If you turn off the constraint, so the particle, the bead doesn't have to be moved on a circle. So suppose that it can jump off the circle, then there will be no more normal force. Yeah. The same thing happens here. If the particle is not required to move along the inclined plane, then the normal force is 0, right? So in both two cases, the normal force acts as a constraint force. Yeah. And the interesting observation here that the normal force in these two examples the normal force is always perpendicular to the displacement. So in this case, the displacement is along the inclined plane. The normal force is perpendicular to the inclined plane. Here, the displacement is along the tangent of this this circle. The normal force is perpendicular to that tangent. Okay, so we can see that the force of constraint, yeah, is always perpendicular. Well, in most cases, the force of constraint is perpendicular to the displacement, and this will have consequences. This will have a interesting consequence later. Yeah. All right, so I can have many other constraints. Yeah, for example, you can see that we have a bouncing ball. Yeah, a ball bouncing on the ground. Yeah, this is ball of mass m. It bounces back and forth. What is the constraint here? Well, the constraint is that the ball can only move along this floor or on the floor. Yeah, so now the ball is it not only it can move along the floor, but it can move jumping off the floor, right? But it cannot move below the floor. Yeah, well, it cannot move below here. So if this is the y direction, this is the x direction. Yeah, so the constraint imposed here is that the y can only have 0 or positive. Yeah, so this is the constraint. Or maybe I have, like, for example, a gas, a container of a chamber of gas molecules. Yeah, I have particles of gas moving back and forth. Yeah, in any random directions. They are moving back and forth. They are in any random direction imaginable. Yeah. What are the constraints here? Well, the constraint is no matter how complicated their motion is, they can only move along inside the chamber, inside the container. Yeah. So the constraint is that Ri is xi, yi, and zi, and I is the number of particle, the ith particle. So the x, y, and z position of any of each particle cannot be bigger than the size of the container. Okay, the size of the container. Let's say that the size is just this is the length, this is the width, and this is the height of the container. So the particles cannot move outside the container. Okay, so this is also another constraint. So now basically we can classify constraint. Let me just put, I have still the last 4 minutes. Let me just classify the constraint. Yeah, the constraint can be classified into 2 terms. Well, first it's called holonomic. And the other one is non-holonomic. What is holonomic? Well, holonomic is every constraint that can be written, can be expressed as an algebraic equation. So let's say f is a function of constraint, and f depends on the coordinate of each particle or each member of the system. Let's say we can always write down the function to be algebraic like this. Okay. Further, holonomic and also non-holonomic constraint can be classified into what we call the scleronomous scleronomos. This means time independent, so this doesn't depend on time, and rheonomos if it includes time. So if time is included in here, so this is called rheonomos. If there is no time dependence, it's called scleronomos. So what is non-holonomic constraint then? Well, non-holonomic constraint is everything that is not holonomic. So for example, the last two examples I just described, the constraints are non-holonomic. Because why? Because those constraints are expressed in terms of inequality. Okay, so this is inequality. So every constraint that is expressed as an inequality, yeah, the constraint is non-holonomic. Okay, but that's not all. That's not all. Even if you have an equality constraint, but the equality constraint cannot be written as like this, it's also non-holonomic. Okay, so non-holonomic is far more general than holonomic. For example, it's greater than something. Yeah, this is a type of non-holonomic constraint. Or we can have equation like this, but not algebraic. Yeah. We can have derivative equation, yeah, or differential equation, but the differential equation cannot be integrated into an algebraic equation. In other words, we have a non-exact differential equation. So if the constraint is expressed in terms of non-exact differential equation, that is also non-holonomic. Okay. Now, if you have holonomic constraint, obviously you can take the differential of the function. So we have df is equal to 0, right? Now, f is a function of r and t. Okay. Suppose that it is rheonomous. In general, it is rheonomous. And t, yeah. So it's a function of multivariable. So now I can express this as the gradient of f, right? Dot dri plus df dt times dt, right? This is equal to 0. So if you can see, this is a type of differential equation. So holonomic constraint can also be expressed in differential equation. The difference of holonomic from non-holonomic, if it is expressed in differential equation, is that for holonomic, the differential equation is exact. In other words, you can always integrate this to get that. Okay. So in general, holonomic constraint can be written like this. Well, holonomic or non-holonomic constraint can always be written like this. Plus b of dt is equal to 0. Well, this expression is what we call the Pfaffian form. Yeah. Pfaffian form of constraint. All right, so I think I can stop here. I'm going to continue on Monday on the next topic. Question?
No, sir.
Okay, if there's no question, we can stop here. Yeah. We can continue on the generalized coordinates and maybe principle of virtual work on Monday. On that, why Monday? Because on Wednesday I have something to do outside the campus. I cannot teach just for the one full day. Yeah. So let's meet on Monday and Friday for next week, okay? And
Okay.
it's be on it's gonna be offline.
Okay.
Okay, thank you very much. If
Thank
there
you.
is
Thank you, sir.
no further question,